Welcome to this presentation on ideal gas mixtures and mixture processes. Here's where we're at in the forest. We've done the thermodynamic relations. That was the equations of state, refrigeration system, power system. So ideal gas mixtures. And what we're going to find is this is very similar to stuff we've already done, but we haven't done mixtures of gases. We've always done one gas and mixing that one gas. So now it's going to be multiple gases and seeing how we can do that. So here's the kind of a simplified form. Again, this is a closed system. We'll be also looking at open systems. I'll just draw it here real quick. But so here, as a closed system, we have gas 1, some number of moles of gas 1, some number of moles of gas 2, etc. In this case, they might all have some pressure for the mixture, a temperature mixture, in this case, a constant volume, and a boundary. And again, we'll also look at ones that are flowing systems. So we might have some black box, as it were. We'll have one stream going in, say CO2, and we'll have another stream going in, say argon, and then we'll have a mixture of those two coming out. And again, we'll look at the analysis on all these pieces. So that's what we're moving into. Again, we've done all this where each one of these items that are going in here, this was air and this was air, and maybe it was different flow rates. And then it was all air coming out, or this was steam and this was liquid. Well, there was water coming, and then we had some type of quality here. Again, this time it's different stuff and it's all gases. All right, so that's what we're looking at as we move into this. So what I'm going to do is I'm going to do some examples, and we'll do some of the terminology along the way. So if you can get the handout will have a listing of all the variables that we're going to be using. So there's a lot of introduction of some new stuff, so you can follow along with that. Again, glance back at that, maybe do a split screen, but I'll try to introduce them as best I can as we go through the problems. All right, here we go. So here's example number 1. We're going to have a gas mixture at 50 degrees Fahrenheit and 1 atmosphere pressure. It's all going to be enclosed in some container. And what we're going to basically do is just have a molar basis. Again, I'll talk about what this means on the next slide as we break this down. But 20% argon, 35% CO2, 45% oxygen. And we want to determine the analysis in terms of mass fractions. So that'll be an introduction piece about what that is. We want to find the partial pressure of each component in PSI. So kind of familiar, hopefully, from fluids where you've heard that before. And then also we want to calculate finally the volume occupied by 10 pounds of this mixture in feet cubed. All right, so let's go ahead and get into that. All right, so for this first part here, we want to find the mass fraction analysis of what we have here. But first of all, we need to understand what we have. So we were told we were given a molar analysis. All right, so as we look at that, let's break this down. I'm going to use I as for indicate all our components to be very generic. And what we're going to be finding is Y sub I. All right, or this is the information they actually gave us. So Y sub I is the number of moles of a given component. All right, so here for the first one I'll put in here, this is argon. So they gave us argon. So the number of moles of argon divided by the total number of moles in the mixture. That is what the mole fraction is. Y is mole fraction, and for sub I is of that particular component. So for argon, the mole fraction of argon that they gave us was 0.2, right? 20%. When they say molar analysis, that they're telling you how much, what mole fraction of argon is in the mixture. For CO2, they told us it was 35%, so that's going to be 0.35 is the mole fraction of CO2. And for oxygen, it was 45%, so that's 0.45 for the mole fraction. Now, what they wanted us to do is to get this on a mole fraction basis. So we basically want to move from a mole fraction to a mass fraction. So a mass fraction is denoted by MF, and then I'm going to do sub I because we want the mass fraction for each component. And the mass fraction is simply the mass of each component divided by the total mass of the mixture. All right, so that's stuff we can come up with relatively easily once we know what we're doing. So that's what our objective is for today. All right. So let's start out again. This is a nice table thing, just again to learn all the lingo here with the vocab that we have. So again, I'll have all the components under I here. So I'm gonna put argon by itself, and then we'll come through and do the other ones. But we want to look at the number of moles we have of argon. So to break this down, to make this easier for us, we're going to start out by analyzing 1 pound mole of the mixture. All right, and this will make things a lot simpler, as you'll see here. So analyzing only 1 pound mole of the mixture, argon, what would be the number of moles we have of argon? Well, if the mass fraction, or sorry, the mole fraction is 0.2, if we take 0.2 times 1 pound mole of mixture, because that would be this N value here, guess what the number of moles is for argon? Yeah, it's just going to be 0.2, right? So that was kind of strategic why we did the 1 pound mole. So if we have the number of moles of argon in a 1 pound mole mixture, so 0.2 moles, and we multiply that by the molecular weight. All right, so molecular weight is going to be in pounds per pound mole. Maybe over here I should put this is pound mole. All right, the molecular weight we're going to get from table A-1. So for argon, that's 39.94. And I'll write this down below here so we can remember here. This is all from table A1. Now I'm writing it down low because I'm going to fill in with the other ones after we get there. All right, so what do we have now? If we take the number of moles that we have of argon and we multiply it by the molecular weight, what do we get? So we get pound moles times pound per pound mole. We're going to end up with just pounds. So what we end up getting is the component mass of argon in our mixture. All right, so we take that and we multiply 0.2 by 39.94, and we're going to end up with 7.988, and that's going to be in pounds. All right. So that looks, well, let me get rid of pounds here. We'll just put that up at the top here. So let me undo that, and we'll put it up here. So there's in pounds. All right, and then we can get the mass fraction. So the mass fraction of our component, but what we need for that, again, is mass of the component divided by the total mass of the mixture. Well, we can't get the total mass of the mixture until we know all the masses here. So we need to calculate the component mass for CO2, and we need to calculate the component mass for oxygen. So let's go ahead and do that. So we'll put down here CO2, extend all these lines here. So for CO2, again, going back here, the number of moles is going to be 0.35 pound moles in our 1 pound mole mixture. The molecular weight from table A1 for CO2 is 44.01 pounds per pound mole. And if we multiply those together, we're going to get 15.404 pounds. For oxygen, number of moles is going to be 0.45 pound moles of oxygen in 1 pound mole mixture. Molecular weight is 32.00, and if we multiply those together, we get 14.400 pounds. All right, so if we sum all those up, add all these up, we're going to get 37.792 pounds of our mixture. So if we have 1 pound mole of this mixture, it would come out to be 37 pounds, right, on a mass basis. So now if we go and do this, we do find the mass fraction. So we're going to divide, and for argon case, we're going to divide our 7.988 divided by 37.792. We're going to come up with 0.2114 For CO2, we're going to get 0.4076, and for oxygen, we're going to get 0.3810. So very interestingly, right, molar basis versus mass basis. Molar basis here, we got CO2 is 0.35, oxygen 0.45. Oxygen takes up more space, as it were, on a molar basis. Whereas over here, oxygen is at 0.38 and CO2 is at 0.4. So CO2 is actually taking up more mass in that particular mixture. So as we move forward, I wanted to highlight this because, again, here's the mole fraction and here's the mass fraction. And both are very important in mixtures. And when going back to chemistry for 2 years for some of you, or most of you, I think, we have the moles are very important as we deal with mixtures, and mass is very important as we deal with mixtures. So we're going to have to be able to work in both realms as we solve these types of problems. All right. I just want to show you one other thing that you can do here with the to help with this solution, finding this value here for the total mass. If we would want to find the overall mole fraction, or I'm sorry, the total molecular weight of our mixture, let's look at that. So if we had the finding the molecular weight, we could take the mole fraction of argon, which is 0.2, and we could multiply that by the molecular weight of argon. All right, and then we can add the mole fraction of CO2 and multiply that times the molecular weight of CO2, and then finally the mole fraction of oxygen multiplied by the molecular weight of oxygen. And multiplying and adding all those together, we're going to come up with 37.792, not pounds, but pounds per pound mole. All right, but check it out. See, it's pounds per pound mole, but what was this? The analysis we did up here was for 1 pound mole of mixture. So we essentially multiplied this number by our analysis of 1 pound mole. All right, so there's another way we could come up with this value, right, and then ultimately use that to calculate our mass fraction. All right, so I just want to give you a heads up on that as well. All right, so that's part A. We calculated our mass basis. All right, of items here. Oops, do a little bit too much. There we go. So we got all those values. Now we're going to move on to looking at the partial pressures. Now, before we get into the calculation of Part B with the partial pressures, I want to come back to this slide because I want to highlight understanding really where that partial pressure, when we do our calculation, where it comes from. So if we look at the pressure of one component within this box, all right, one component, using ideal gas, it would be the number of moles of that component times the universal gas constant times the mixture temperature, right, which shows up right here, divided by the volume, which is constant for all the mixtures. So that's the partial pressure of the mixture. Now, I don't want to calculate it that way. I want to calculate with information that we already have from the problem. So if we would look at the pressure here, this partial pressure, and we divide it by the total pressure. All right, so this is the pressure just for one component. So it's going to be less. This pressure is going to be less than the total pressure because we're only looking at the number of moles of that particular component. So if this is oxygen, we just look at the number of moles of oxygen, and that's what we put in when we calculate our partial pressure. So this will give us that pressure fraction there. And so finishing out our calculation, if we had our number of moles times the universal gas constant times the temperature divided by the volume, and we divide that by the total number of moles times the universal gas constant times the temperature divided by the volume, right? Everything's canceling out except for the number of moles, so we have the number of moles of a component divided by the total number of moles. What's that equal to? What's this equal to? Right? We just saw in the previous slide, right? That is equal to the mole fraction. Right? So when we're trying to find partial pressure, if we know the mole fraction, if we know this mole fraction, and we know the pressure for the mixture, we can then calculate the partial pressure of our component. So we're going to do that and make our calculation real easy on the next slide here. All right, so here we go. Now we have a better understanding of partial pressure. If we want to find the partial pressure for argon, all we need to do is take the mole fraction of argon and multiply it by the total pressure of the mixture. And we were told the total pressure is 1 atmosphere. If you need to, go back to the initial slide there and you can see that. And so we can just plug in our values here. So mole fraction of argon was 0.2, and total pressure was 1 atmosphere, or converting over to psi, because that's what we want to solve it, and it's 14.7 psi. So the partial pressure is 2.940 psi. I'm going to get pound force, but we'll just call it psi, right? Psi, right? So there we go for argon. And now we can go back and we do the same thing for CO2. So you got a mole fraction for CO2 and the total pressure, and CO2 is 0.35 for the mole fraction, 14.7 psi. And we come up with 5.145, and that's again in psi. All right, finally, we got the partial pressure of oxygen. The mole fraction of oxygen times the total pressure, and we get 0.45 for oxygen, and then 14.7 for the total pressure, and that comes out to be 6.615 psi. All right, so that is our partial pressure calcs. And finally, to finish this off, they want us to calculate the volume for our mixture. If it was 10 pounds of this mixture, so that's a basic ideal gas calc. So we're going to do volume is equal to mRT divided by pressure. So all these things are the mixture values. So the mass we're told what they want. They want to use 10 pounds there. For the specific gas constant, all right, it's going to be 1545 divided by the molecular weight for our mixture, which we found is 37.792. Again, that's the molecular weight for the mixture. And then we have, that's going to be in foot-pound force over pound mass and times degree Rankine. And the temperature, 50 degrees Fahrenheit, so it's 510 degrees Rankine, divided by pressure of 1 bar, or 1 atmosphere, so 14.7, times 144 to get us in pound force per foot squared. All right, so our pound forces will cancel, degrees Rankine, cancel, and pound, mass cancel, so then we'll end up with feet cubed. So our final volume comes out to be 98.5. My pen's being wonky again. 98.50 feet cubed. All right, so I hope that helps kind of set up and introduce all the different items we'll be using as we go through the mixtures. There might be some additional ones as we move through this, but hopefully it'll make sense as we hit them. All right, I got one more example for you, so look for that as well.